Hey guys, Michael Clark here with BAM Weather. This is my third attempt at recording this video, full transparency. We're going to try and go over some educational points with you guys, some different acronyms and different things that we use on a daily basis in our videos to try and illustrate what the forecast is. I always get people going, you know, what in the world do these different things mean? The MJO, the NAO, and all these different things. So what I want to try and do is explain them to you to the best of my ability in this short educational video. So what I've done is I've taken a map here of the entire globe, and I've kind of, typed out where all these different acronyms are located. And these different acronyms really drive the pattern, the weather pattern for the entire world. And so what I kind of want to do here just real quickly is kind of start from west to east and just go over these with you. So the IOD, which is the Indian Ocean Dipole, what this essentially tells us is what the Indian Ocean water temperature looks like. The negative Indian Ocean dipole would look like a cold western Indian Ocean and a warm eastern Indian Ocean. The positive IOD would be the opposite. It would be warm west, cool east. That has significant impacts on the jet stream and the tropical convection for our patterns here in the U.S. Okay, the MJO, which is the Madden-Julian Oscillation, right? That is where different areas of convection and thunderstorm complexes move across the equatorial Pacific Ocean. As those convection complexes or areas of upward motion move from west to east across the Pacific Ocean, it alters the weather patterns drastically. Convection is a fancy term for moving air or thunderstorm activity. Upward motion is a fancy term for areas of low pressure or areas of air that have a lifting mechanism where thunderstorms, rain, and clouds can develop. So the MJO can be through phases 1 through 8, and each phase plays a significant role on how the weather patterns will react really across the world, as that MJO pulse is what we normally refer to them as, propagates. Propagate means to move across the equatorial Pacific Ocean. The next one is EAR. You'll probably see that referred to often in the long-range reports. That's the East Asia rule. What the EAR stands for is basically anything that pops up in East Asia between the Korean islands and Japan will show up in the U.S. 6 to 10 days later. It's an organic forecasting tool or an outside-of-the-box, somewhat of an unorthodox method on how to predict weather 6 to 10 days out. The SOI is the Southern Oscillation Index, and that is the difference in surface pressure between Tahiti and Darwin in the southern hemisphere. And what that will tell us is essentially the differences in pressure between the two different locations and how that will impact the SOI going positive or negative. Big rises or falls in the SOI can result in big cold fronts or big warm spells. ENSO, probably the most popular, it's the El Nino Southern Oscillation Index. Okay, that region of the Pacific Ocean is located across the equatorial Pacific here, from about 180 west to about 80 west here across the equatorial Pacific. And this is the regions where we monitor is the water colder or warmer than normal, La Nina and or El Nino, very important to the pattern. The BSR, which is the Bering Sea Rule, another outside of the box organic type forecasting method. What that essentially does is tell us the pattern in the U.S. 17 to 21 days out. Sometimes it works great, sometimes it doesn't. The PDO is the Pacific Decadal Oscillation. What this means is the word decadal is just that. It's an oscillation that moves typically about every 10 years or so. And that will tell us essentially what the dipole is or what the water profile of warm and cold is in the northern Pacific Ocean. Is it negative or is it positive? It will help determine where areas of high and low pressure may be favored or not favored. The PMM is the Pacific Meridional Mode. This is the temperature of the water here off the southwest coast of the U.S., just north here of the ENSO regions. All right, the negative PMM and the positive PMM can be associated with warmer or colder waters off the coast of the southwestern U.S. In this particular instance, it's a very cold negative PMM at the moment. The PNA is probably the most significant pattern driver for the lower 48 for the United States. It's the Pacific North American pattern driver, and it essentially measures the 500 millibar heights. The 500 millibar heights, I'll get into in just a moment. Quite frankly, or I guess somewhat simply, if you will, here is warmer and positive heights really result in more higher pressure or warmer and drier weather. Lower pressure can result in, the cooler heights. The lower heights result in upward motion and inclement weather, areas of thunderstorms and colder weather and things like that. The EPO is the Eastern Pacific Oscillation. That is just another form here to measure the 500 millibar heights, which I am going to show you. I want to show you this because this is what we're looking at. The 500 millibar heights quite simply just tell us if this is a high pressure area or a lower pressure area. Okay, is this a trough, a front, or is it a ridge, a blocking pattern? Okay, in this particular instance, what we would see here is somewhat of a negative P&A pattern because of the trough here, would result in this eastern southeastern U.S. ridge. In this particular instance, we're looking at a positive NAO, which is the opposite of the 500 millibar ridge. It's a non-blocking pattern. So these simple acronyms essentially correlate to where 500 millibar heights are located. The North Atlantic Oscillation, the Arctic Oscillation, and the Eastern Pacific Oscillation can be in positive or negative phases and help dictate where high and low pressure cells are centered. Okay. The AMO is the Atlantic Multi-Decadal Oscillation, which means it may go back and forth over multiple decades before it changes one way or the other. The MDR is known as the Main Development Region, and that's where hurricanes typically or primarily develop before they strike the U.S. So that's a kind of a breakdown of some of the acronyms. Hopefully that helps you a little bit. Next, I want to dive into a little bit of the local aspect of weather forecasting and kind of how it's done, because I think there's a lot of misconception here into how it's actually looked at and how it's computed and used. This is a look at an hour-by-hour forecast from one of our locations from the weather portal. You'll note that hour-by-hour forecasts generate conditions on the hour every hour, specifically to that location, wherever your location might be. Okay? Temperature of 67 degrees, recommended you not spray, with a southwest wind at 10 to 12 miles per hour. You may be looking at a 10-day outlook that's going to tell you a high of 81, a low of 58. Okay? 76% chance of showers and thunderstorms in the morning. These forecast grids are generated off of 25 miles from a point in terms of a square mile, or in terms of a radius standpoint. So if your forecast location is Indianapolis, you're pulling data in from the 25-mile radius from that point, which means we're forecasting weather for this area in general. Understand, it's very difficult, if not impossible, to forecast weather down to your backyard, down to your field or your specific location. Getting to within 25 miles of a point is about as good as you can really do and still have a realistic weather forecast. You start to get any closer into location specific right down to that address, you're going to notice incredible run-to-run inconsistencies with weather models because it's going to change every time because it's such a small area. So when a weather forecast is generated from most entities, including us, you're going to be looking at a threat assessment within 25 miles of a point. This can also factor in POPs, or probability of precipitation. Within this 25-mile radius, you're going to have a POP. Let's say your forecast, we go here, let's say the forecast for Thursday night is a 33% chance of rain in the afternoon. It's a 12-hour average window in the afternoon. Well, that means that 33% of this circle is going to be looking at the potential for showers and thunderstorms. It's possible that 66.3% of the rest of the circle is not going to be looking, or 66.6%, if you will, is going to be looking at drier conditions. It could be any part of the circle, right? It doesn't have to be one particular part. It's the probability you'll see rain within 25-mile radius, both in the hourly and in the daily. Okay? Hopefully that helps you a little bit. Let's talk about real quick QPE, quantitative precipitation estimates. Those are based on 1 kilometer grids, which when you when you transition a kilometer to a mile, it's 0.6. It's 6/10 of a mile. Okay, let me give you an idea of what the error can look like at 6/10 of a mile. It still can be significant. It can be several blocks. If we're looking at Indianapolis, you've got 4, 5, 6, 7, 8, 9, 10. You've got about 15 blocks within 6/10 of a mile. Rainfall can be drastically different at those points. Okay, it's incredible that we've got it down to 6/10 of a mile, but it can still be drastically different. So while the data is super high resolution and it's really, really neat data and it's cutting edge, it's still prone to error within a half mile of every grid point. Okay, imagine thousands of little squares plotted over this with grid points at 1 kilometer on each one. You really got to start getting down into half kilometer, even quarter kilometer, to start talking about hyperlocal. Okay. When we look at computer models and we talk about QPF, QPF stands for the Quantitative Precipitation Forecast. That's the amount of rainfall a model is forecasting at any given time or any given period out to a certain point, to a certain area, if you will. All different global weather models have different resolutions. 9 kilometers, 13 kilometers, so on and so forth. And what that can mean is that the lower resolution models don't do as good at pinpointing locally heavy rainfall threats. This is a look at the GFS weather model and its high resolution depiction. You can see that it's splotchy in nature and tries to give you a good idea, but if you looked at the next computer run, it would look entirely different. They change every single run. This is where ensembling comes into the equation and can help. We look at multiple different members. Every time we talk about ensembles, the American model has 30 of them. The European has 50 of them. Then they have a control member, which gives each one 31 and 51 different members. Each ensemble member is initialized with slightly different weather variables or weather parameters to come up with a little bit different of a forecast. It's a meteorologist or forecaster's job to determine which ensemble members to use and which models to show you. It doesn't necessarily mean one model is better than the other. In each particular situation, there's going to be a model that has the upper hand as long as the meteorologist is actively dissecting it, analyzing it, making sure it's the best one. You can see there's 30 different outcomes here for total rain over the next 7 days. You have models that range from 0.3 inches to 3.1 inches of rain with an ensemble mean of 1.1 inches. That's why when I show you this map here, it's important to note that it's tough to nail down a rainfall forecast. Very difficult. You've got, at any given time, over 100 different solutions if you look at the American, European, and Canadian weather model data. That's what the individual ensemble members do. They'll produce rainfall, temperature, snowfall, pressure, all kinds of different variables to help a meteorologist make their forecast. Last but not least, I want to explain to you what below normal and above normal means, or +1, -1, +3, -2, so on and so forth. Simply, these numbers are the temperature departures from normal. So if you're -3 to 5, you're going to be 3 to 5 degrees cooler than average for the 6 or 7 day period here to start out the month of June. If you're +5 to 8, you're going to run 5 to 8 degrees above the average to start out June. Okay? Precipitation maps, percents of normal. Let's say you average 1 inch of rain per week. That is exactly 100% of the normal. If you were to be forecasted to see 150% of the normal rain, you'd be looking at 1.5 inches of rain. If you were forecasted to see 2 inches, or 200% of the normal, that's how that works. Okay, so if you're in the yellow and you're at 75% of the normal, it doesn't mean it's not going to rain. Essentially, it means you could still get 3/4 of an inch of rain for that week, but you're technically only going to be 75% of the normal 1 inch of rain in that period. Okay? EC on these means equal chances. It means there's not enough evidence to go below or above normal for that time period. All right? Same can be said for the weeks 3 and 4 and their maps. Below normal simply means be in or below normal. That's just what it means. It just means you're going to be cooler than average, or in the same sense, it could be your below normal precipitation. MAN would stand for much above normal or much below normal. The EAN or the EBN you see on these maps can stand for extremely above normal or extremely below normal. So you're looking at just a larger departure from normal, okay? So I just want to take some time today and try to explain this stuff to you. I could obviously do a video for probably 3 or 4 hours and then go through all these variables in detail, but I wanted to try and give them to you as quickly as I possibly could. It's very, very difficult and sometimes impossible to nail down forecast variables and parameters down to specific locations. And that's why it's important you understand the radius within a point and you understand how ensembling works and how this stuff really, really works, right? It's difficult and it's not a perfect science. It's evolving. We learn every day. The technology gets better every day, but we are literally trying to predict the future, and that can be very difficult. If you guys have any questions, feel free to contact us at any time, info@bamwx.com, or you can send us a direct message on any of our social media platforms. Hope you have a great day.